Alright, our lesson today is on special right triangles, a bit of a introduction, and we are going to explain how the relationship between angles and sides exists in a special right triangle. And we're going to do so through a little discovery task. So there are a few things I am going to need you to get, and here is just a picture of what you will need. Everything has been provided for you, so you'll need your Cornell notes, you'll need the two cutouts, colors, glue stick, and then pencil, ruler, and a scissors. So at this time, what I would like you to do is to go ahead and cut out the two figures, and then we will get started. So pause your video out here and go ahead and copy the heading to your note-taking guide. So we're going to start out with the shape. So first of all, let's identify what this shape is. Okay, so over here at the side, I'm going to write identify the shape. And at this point, I'm sure we all know that this is a square. So what I want you to do is take a look at the square, and we are going to be thinking about certain properties that the square has. And while you're doing that, what I would like you to do is go ahead and take your cutout, and I'm going to want you to go ahead and double it from one vertex across from the other vertex and join them together to make a triangle. And what I'm going to have you do is stick this triangle onto your paper. So this is where your glue stick comes into play. Alright, so first double your square, grab your glue stick. It doesn't matter which side you want to glue, but I want you to glue only half of this triangle, of this square, my bad. Okay. And it does not matter how you decide to stick it. The only thing I do ask is that one side stays, you know, that can be folded back and forth. Okay? Okay. Alrighty, so what's the first thing we're going to do? I told you to be thinking about the different properties. So down here at the bottom of your paper, on the left-hand side, I'm going to label this side properties, okay? And what I want you to do is pause the video a second, and I want you to come across some properties, some typical properties that you know that a square has. And I want you to list a couple of bullet points of those properties that you know. So please pause, because we will then gather together and decide what some of those properties were. So after you have paused it, probably a few of the properties that you came across were that the square has equal sides, they're all of the equal length, that there are 4 sides, that it's a parallelogram, and that all angles are 90 degrees. So these are some examples of responses that I've had from students from in the past, and so you may have had different wording or additional ones. Like I said, hopefully you took the time to try and guess some on your own and then look to see what was written. So let's do some labeling based on what the properties that you came across. So one of them was that the sides were all equal. So let's get a ruler and show how we would show on a diagram that all our sides are equal. So if I came over here, I don't know the exact measurement of the length of this side, but I can say that from here to here, it is some length, let's call it x. And because we said that all sides are equal, we can go ahead and say if this side over here is of length x, then this side over here as well has to be a side of length x. Okay, so that right here takes care of one property. The other property is that, well, it was a parallelogram, and we could see that these segments have the same slope. They're either undefined slope or they have a slope of 0. That was another property you could have given. The angles are all 90 degrees. So if you recall from geometry, we always use squares to depict the 90-degree angles. So we'll do that. Now, this is the square, but what we noticed is that when we take a square and we fold it over in half from vertices that are sitting across, that a triangle appears, okay? And this triangle earns some properties from the original properties of a square. So we've already come across that all sides here were of length x, and all angles were of angle measure 90 degrees. And right here across this line, I'm going to go ahead and put a dash line to make a point. We folded it over here, and we discovered that something is going to change, okay? Well, let's talk about the lengths of the sides of the triangle. What do we know? Well, we noticed that this side right here, nothing changed in its length. It was unaffected. So as far as the length of this side of the triangle, it still remains an x. The same can be said about this side. Notice that this side and this side were the same length. Nothing was changed there. That side remained the same length x. So if you wanted to, we could go ahead and label this x right here for visual purposes, if you wanted to do that, just to give yourself a better visual. So I'm going to come ahead and do this right here and this right here and do the same thing here. Okay, but something did happen to our angles. Okay, so maybe you're already noticing that this angle remained unaffected. It still remained a 90-degree angle, but something did happen with these. Okay, what do you think happened? So if you're saying cut in half, it sure did. This is becoming a 45 degree. This became a 45 degree. And I'm just going to go ahead and mark this even though we know it. But this also ended up being a 90. And if you remember the properties of a triangle, they must all add up to 180 degrees as far as the angle goes. So we have the angle measures. We have these two sides. But this side right here, we don't know what the length of that is. That is unknown. And so we are going to have to figure out the length of this side which we call what? What is the length of this side called? Well, we just actually went over that the other day, and we need to find the length of the hypotenuse. So let's go ahead and do that. So what is used to find the length of a hypotenuse, or a missing side of a right triangle? Well, we resort to the Pythagorean theorem. So let's go ahead and do some algebra using the formula for Pythagorean theorem in order to find the hypotenuse. So the formula for Pythagorean theorem, as you guys know, is a squared plus b squared equals c squared. But as I shared with you before, personally, I like to use leg squared plus leg squared equals hypotenuse squared. Now we knew that the legs were given, and we know these are legs because the legs are what form the 90-degree angle of a given right triangle. So that was given to us in the length of x. So a leg squared, x squared, plus the other leg is an x squared. And the hypotenuse, we do not know what it is. We're going to use the letter h for hypotenuse. X squared plus x squared. There are two x squareds now, if you combine the like terms, and that equals to hypotenuse squared. Since we're solving for hypotenuse, we need to get rid of the power of 2, and we need to what both sides? We need to square root. So I'm going to square root this side, and I'm going to square root this side to get the h to be isolated, and then I will simplify. The square root of 2 would give me a decimal, so I'm just going to leave square root of 2 alone, just like this. And the square root of x squared is just going to be an x. It comes out of the square root. Square root of x squared is just x, but we usually write it where the x is in front of the square root. Okay, so x square root of 2 equals the h, which means x times square root of 2 equals h. So I can come back up here to my image, and now I know that the length of my entire hypotenuse, so I'm going to draw a little arrow here again to show the visual, is x square root of 2. So here is how the special right triangle ratios for a 45, 45, 90-degree triangle came about. So over here in conclusion, we're going to write, bring my dot cam a little bit lower. We are going to write down what we have discovered. Therefore, this is the symbol for therefore, a 45, 45, 90-degree triangle will always have ratios of x, x, and x square root of 2. So this simply means the following. Let's go back to this image. I'm just telling you that if I know the length of this side, I automatically will know what the length of this side and this side is if it's a 45, 45, 90-degree triangle. Because if this is length 5, I've already established that this has to be the same length as this, so this has to be 5. And then this side has to be whatever the length of this and this is times square root of 2, so it would be 5 square root of 2. So if this is 10, this has to be 10, and this has to be 10 square root of 2, and so forth. Okay? So what are we going to do now? Well, I basically had just did a little suggestion as far as adding color to our little diagram. Was I had asked for you guys to take the time and just color it here just a little bit for me. And so you can pause your video and go ahead and do your coloring. And we're going to repeat the task, but with the other cutout. Let's see what you guys discover with the other one. All right, so there we go. All right, so let's go to the other side. So I want you to repeat the same thing that we just finished doing, but now let's work with this shape. So go ahead and identify what that shape is. Okay, so did you identify the shape as an equilateral triangle? This is what this shape is. So again, you are going to fold this shape that I've given you, and we are going to stick it onto our paper. Okay, so we will fold it like this. So I guess if you're holding your equilateral triangle like this, bring them together like that, the two vertices, and convert it into a different triangle, this time a right triangle. Okay, and again we are going to get our glue stick and stick this one more time and do some discovery here. So glue half of it, whoops, and there we go. So be able to move the flap over. Okay, so be able to do that. Okay, so again, I would like you to seriously, this time, if you really didn't pause the video the first time around when we did the square, I want you to pause the video and come up with your own properties for an equilateral triangle. What do you observe in this shape? Come up with your own, and then we'll see what I've put as possible answers that other people have done in the past in my class. Okay, so here are a few properties again that have come up in the past when teaching this. So the first, they identified three sides, do that it's a triangle. They have said that all angles were equal, and so they were able to determine that it had to be 60 degrees because 180 divided by 3 ends up being 60 degrees. All the sides were of equal length, and that's why it's equilateral, equal sides. And then last, the altitude is bisecting the base and the angle. The altitude being this right here. If you recall from geometry, the altitude always forms a 90-degree angle with the base. So let's draw that dash, and we can go ahead and establish that this will be a 90-degree. So what we want to go ahead and do is label our triangle with the given information. We said that all sides are going to be of length x, so we can do this just like we did with the square. Take your straight edge, this side is length x, this side as well is of length x, and this side as well. Okay, and put this X in a better position. All right, so all the three sides are length x. We also said that all the angles were 60 degrees. So let's do our little curvature here and write that it's 60. We know this one up here is also 60, and this one here is also 60. Okay, but then what happens? Our equilateral triangle converts into a right triangle. A right triangle because due to the altitude, we know this angle here is going to remain 90 degrees, right? Now, we're looking at this angle down here. We notice that it's not changing in measurement. So we know that the bottom angle down here, this base angle, remains 60 degrees. But what is happening up here? Okay, what happened? What did that altitude do? Well, it bisected that angle, and bisects means to cut in half. So this angle became a 30-degree angle. Again, 30 plus 60 is 90, 90 plus 90 is 180. So we have a triangle here. And instead, this time, just go ahead and color right off the bat. Okay, so hopefully by now you're finished coloring. And yes, I do want you guys to color, add a little color to your life. Okay, so we have a 30, 60, 90, and do we have all the lengths of our sides just like we did with our square? So three sides, here we go. This side, we're good to go. We know it's length x. This side here, well, doesn't look like we know it because it was, the length of this entire thing was x, but what happened? So this is no longer x, but half of the x, okay, because we got bisected due to the altitude. So let's make sure we make a point in our diagram to show that the length of this new side from here to, whoops, sorry, from here to here is no longer x, but half of x. Okay, or x over 2, if you want to write it as x over 2x as well. Okay, half of x or x over 2. All right, so we've got this side and this side. How about this side? Well, there's no relationship that easily can help us find the missing side like this one was. That one was pretty obvious. So again, we are going to have to resort to our Pythagorean theorem. So I'm going to come down around right here, and we're going to use Pythagorean theorem all over again to find the length of our missing side, which in this case, notice it's not our hypotenuse this time. Okay, this time it is one of our legs, okay, because our legs are the ones that form the 90-degree angle. We have our hypotenuse already. So leg squared plus leg squared equals hypotenuse squared again. All right, so leg squared plus leg squared equals hypotenuse squared. We know one of the length of our legs is half of x, so I'm going to put that here, 1 over 2x plus. I don't know what this leg is, so what letter should we use? Let's not use L. Let's use, you know what? Let's use M for measurement. So we're going to call this M for now. Okay. So half x plus m squared, so I don't know what that is, equals, what is my hypotenuse? It was length x, so I'm going to put x and then the squared. Oh, I forgot the squared here. Alright, so let's simplify. What is half x times another half x? Well, that's going to be 1/4 x squared 1/4 x squared plus the m that we're looking for equals x squared. I need to isolate my m squared. I need to solve for it, so I need to move this over. So I'm going to subtract 1/4 of an x squared on both sides. Okay, so 1/4 x squared minus 1/4 x squared becomes a 0. My m squared comes down. And what is a 1x squared minus a 4th x squared? Think of a 1 minus a 4th. Well, that's 3/4 x squared. So 3, I'm going to write it as a stacked fraction like this. 3/4 x squared. And what's our last step to isolate our m? Well, we need to get rid of the power of the 2, so we square root both sides. Square root m squared. We need to square root this entire thing on this side. And so now my m is by itself. And I'm going to square root each one of these terms, okay? So the square root of 3 would give us a decimal, so we're going to leave it as square root of 3. The square root of 4 is just a 2. And the square root of x squared is just an x. So there's the length of our altitude. So let's come up here, and we're going to write in our missing side, m for missing, is square root of 3 over 2x. I better scoot it over. Can you see what I'm writing? Okay, square root of 3 over 2x. Okay, so let's write down our conclusion down here. We have discovered our 30, 60. This is a 30, 60, 90-degree triangle. And the ratios of our 30, 60, 90 would be always. See, there's our 30. Sorry, there's our 30. Across from 30 is the half x. So I'm going to put the half x over here. 1 over 2x. Across from 60 is the square root of 3 over 2x. So square root of 3 over 2x. And across from 90, across, is an x. Now, what mathematicians decided to do was, you know what, they didn't really care for having fractions as their ratios. So they wanted to get rid of the denominator value, but maintain the legitimate ratios of their discovery. So what is the best thing to do? Well, if we multiply 2 to every single one, it would simplify and get rid of those fractions. Well, 2 times a half would just be an x. 2 times square root of 3 over 2 times x would just be, again, the cancels the 2. So that'd just be square root of 3x or x squared root of 3. Let me do that. Usually we put the x in front of the square root. So x squared root of 3. Again, the 2 got canceled. And if I multiply x by 2, I'm going to end up with 2 times x. Okay? So, just like I was showing you with your square, if I know the length of one of my sides, x, I will know the length of the other two sides. Let's say x is 5. So if I know the length of this side to be 5 units long, this one right here is going to be 5 times square root of 3 over 2. And then down here, it's going to be 5 over 2, or 1/2 times 5, which is 5 over 2. Okay? So these ratios are very, very helpful when we work with special right triangles. So the summary basically is that I didn't want you guys just to merely memorize these ratios and just go on your merry way. I wanted you to understand where these were birthed from, for lack of better words, okay? So x square root of 2. Yes, I would like you to memorize those ratios, but also understand that this came from a square, and now you can remember the task of actually doubling that square to convert it into a triangle, and remembering the properties of the square that helps you remember this ratio, and how the 30-60-90 ratio came about. You will attribute it to working with your equilateral triangle, okay? And again, have that image of you working out this hands-on activity, okay? So we will learn in our next class session how to use these ratios to quickly figure out the lengths of missing sides of any given special right. Thank you so much for listening, and don't forget to turn in your final product.